Consider a few real-world problems like predicting the price of a house, or determining a credit card score, or predicting the number of subscribers I'll have by 2020. All of these involve predicting a value and are hence regression-type problems. Each one of these problems has a set of input variables called covariates that are used to predict an output response variable. Covariates go by other names like features or independent variables and predictors. The relationship between these input and output variables are determined using a statistical learning method, specifically for regression in this case. In this video, I'll be talking about a parametric regression method called linear regression. So, parametric, what is that? It means that the learning method uses a fixed equation form that establishes the relationship between the dependent output variable and the independent covariates. Parametric regression models take the general form y is equal to f of x plus epsilon, where y is the predicted output variable, f of x is an unknown function, and epsilon is the error term that is independent of the covariates x. Different regression models use different forms of the function f. In linear regression with one covariate x, it takes the form beta 0 plus beta 1 x. The parametric form has thus reduced the problem of finding a relationship between the covariates x and the response variable y to determining two coefficients, beta 0 and beta 1. This makes things a lot easier. Linear regression makes an estimate of these coefficients. Such estimates are represented with a hat over the variable. So linear regression's objective is to determine the value of these coefficients based on the given data. Note that the epsilon term is not a part of this equation because this is the linear regression estimate. Like I said before, epsilon is independent of x and cannot be determined by regression analysis. So in other words, even if we were to somehow create a perfect linear regression model, it would still have some error epsilon. For this reason, it is also known as the irreducible error. In order to estimate these coefficients, we want to minimize the difference between the actual value y and the predicted value by the model, y hat, for every sample x. This difference is called the residual error, e. Now, don't confuse this residual error e with the irreducible error epsilon. By definition, epsilon is a part of the residual error. Say there are n sample data points where the residual error of the ith sample is ei. Our goal now is to minimize the sum of squared residuals, or RSS. We take the squares because the magnitude of the error matters, regardless of whether our model outputs a higher or lower prediction. I rewrite the equation using argmin. So what is that? What argmin actually returns is the values of beta 0 and beta 1 that minimizes the residual sum of squares. Let us substitute our label estimate y hat and expand the inner bracket. We now find the stationary points by differentiating the RSS with respect to beta 0 and beta 1 separately, and then equating both to 0. Differentiating with respect to beta 0, we use simple differentiation rules. We then get rid of the 2. We then bring all the terms that are not beta 0 to the other side of the equal sign. And then we substitute the sum divided by the total samples n with their respective means. We get beta 0 hat is equal to y bar minus beta 1 hat x bar, where y bar and x bar are the sample means. Now differentiate the original equation with respect to beta 1 using simple partial differentiation rules. Bring the 2 onto the other side. Expand the bracket multiplying xi to all terms. Now substitute beta 0 hat that we found previously. After some simplification and bringing non-beta 1 terms to the other side of the equal sign, you get this equation. Replacing the sample sum with their respective means, we get the final form of the coefficient beta 1 estimates. Beta 0 hat and beta 1 hat together define the least square coefficient estimates. Now, given some data points, which are the covariates xi and the response variables yi, we can determine the coefficients and plug the final betas into the regression equation. After that, we can compute any y given any unseen x. Like compute the price of a house given the cost of living index of a city as the covariate. This is linear regression, but most real-world problems have many covariates. In such a case, we would want to use the extension of linear regression called multiple regression. This is another parametric regression method, and since it's parametric, it also has a general form y is equal to f of x plus epsilon. But this time, f of x takes the form of the sum of products of p covariates and coefficients. That is beta 0 plus beta 1 x1 plus beta 2 x2 all the way up to beta p xp. So the estimated value of the response variable y is given by this equation. This is exactly the same as was with the case of linear regression, with just more covariates. To compute the response variable for a given sample iteratively, we would need p-1 multiplications and p-1 additions. So for n data samples with p covariates each, we would thus have n times p-1 the whole square such operations. However, when dealing with such a large number of values and operations, computers tend to perform more efficiently with matrices, so we'll represent multiple regression in its matrix form. I'll use the convention that any matrix or vector is bold-faced in order to distinguish them from scalar quantities, as shown. From our multiple regression equation, we can see that y is equal to x beta plus epsilon, and y hat is equal to x beta hat. Here, y is an n cross 1 matrix, or an n-dimensional column vector. X is an n cross p plus 1 matrix. It's p plus 1 and not p because of the additional intercept multiplican, which we take as 1. Beta is a p plus 1 dimensional column vector, and epsilon is an n-dimensional column vector. We know this relationship is correct by substituting the values and performing matrix multiplication and additions in place. We can verify this relationship by substituting the values and performing matrix multiplications and additions. You can see that each entry of the vector takes the multiple regression equation form. Okay, so now the question is, given this matrix form, how do we compute the coefficients? Well, it's exactly the same way that we did for linear regression, that is minimizing the least squares criterion, but this time for matrices. Remember how we did that before? We need to minimize the sum of squares of residuals. So let's consider the matrix form of the residuals E. It's pretty easy to show that it is an n-dimensional vector form, which isn't much different from its scalar form. It is the vector of residuals for all n samples. This is also equivalent to the difference between the vectors y and y hat. The residual sum of squares can be rewritten as a product of E transpose times E. We now replace E with y minus y hat, and then y hat with x beta hat. We can then expand the matrix transpose. Remember that AB transpose is B transpose times A transpose. We multiply the terms to get rid of the brackets. As with the least squares method for scalar values, the goal is to find the value of beta that minimizes this RSS. Before we go there though, I'll touch up a bit on matrix calculus, specifically differentiation. If X is an m cross 1 vector and A is an n cross m matrix that is independent of X, then we can use the following few formulae. If we have some y that is equal to A, then the partial derivative of y with respect to x is 0. If we have some y that is equal to A times x, then the derivative of y with respect to x is just the matrix A. Now, if we have it the other way around, then it is A transpose. And the last rule is that if we have y equal to x transpose AX, then its partial derivative with respect to x is 2x transpose times A. We'll use these 4 formulae for minimizing the RSS. Recall that a stationary point corresponding to a minima is formed when the slope at that point with respect to a variable is 0. So we need to find the estimate beta for which the partial derivative of RSS with respect to beta hat is 0. We expand the partial derivatives to every term. The first term is independent of x, so their derivative is 0. The second term has the second formula form of y is equal to a beta hat, so its derivative is just a, that is y transpose x in this case. The third term is of the form y is equal to beta hat a, so the derivative is a transpose, or x transpose y the whole transpose. And we have the last term that has the form y is equal to x transpose ax. So the derivative is 2 beta transpose a, or 2 beta hat transpose x. We expand the transpose and then put the negative terms onto the other side. We now cancel the 2 from both sides and apply x transpose x inverse on both sides. And finally, we take the transpose on both sides, just to get the beta hat term on the left. Note that x transpose x is symmetric, so transposing the product square matrix doesn't really change its value. And in the end, we are left with beta hat is equal to x transpose x the whole inverse times x transpose y. What I can do now is give you a set of sample features and labels. Then you can estimate the coefficients, determine the unknown equation f of x, and use this to predict the value y hat. Such as like in the case of determining the price of a house, but this time not only based on the cost of living index, but also on, say, crime rate, population, distance to the closest supermarket, and a host of any other features you want, or any other features that you think is relevant. Of course, assuming that there exists a linear relationship between a predictor and a response variable is usually an oversimplification. Such rigid regression is the very definition of a high bias problem, which in turn means a higher mean squared error. We'll discuss more flexible methods in the future videos. However, understanding these fundamentals of exactly how coefficients are estimated is important as we delve further into statistical modeling. And, well, that's all I have for you now. Hope you guys know a little more about linear and multiple regression. If you thought this content was useful, share it with your friend. You know, the one that has a stats exam tomorrow and is trying to binge watch YouTube tutorials. Yeah, him. Subscribe to my channel for more amazing content, and I'll see you in the next one. Bye.